So in this video, I thought I would describe KO itself. KO is the 1D version of the Lagrangian formulation using mass, momentum, and energy. And it's a finite difference scheme. And if you scroll down on page 191 here of Mark Wilkins' book, in Appendix B, you'll see the formulation that he derives for planar 1D, cylindrical 1D, and then the spherical geometry. So this is good for those three geometries in 1D. So here's the equation of motion, here's the conservation of mass, and then here's energy. And then in order to close this, we need the equation of state. And in order to put in some irreversibilities, he's got artificial viscosity here. So, and here is your plastic flow rule. So that's the mathematical formulation, and then he also presents this finite difference equations where he's taken the same numbering scheme. So you can see here this is number 1, this is 2, and so forth, 3, 4, 5, 6, 7, and then in appendix 1b he's got the finite difference scheme where he's got indices j plus a half and j plus 1. So this is 2 steps in time, in forward time. Unfortunately, he used these half steps. I'm sorry, that's in space. The j indice is for space, and the n indice is in time. And again, he used half integers, which is not very easy to code in Fortran. So you'll see in my Fortran code that for any j plus 1 or n plus 1 forward step, it's actually n plus 2 in the Fortran code here on the right, and then any j plus a half or n plus a half is an n plus 1 in the Fortran code. But what's beautiful about this is that he's gone ahead and done the discretization for you here, and as far as I can tell, he didn't get any indices wrong when I went through it a little bit myself. But if we just scroll on down here, you can see he's got everything, the entire formulation discretized, including the time stepping using a Courant stability criteria, and then a suggestion for inner and outer boundary conditions, meaning the left and right side in Cartesian, or in spherical, the inner or outer kind of makes more sense. So he's even got how to open and close voids for SPAL. So take a look at this. It's really quite well done. And I'll show you then how I laid it out in the Fortran version that I wrote. So here's the Fortran version here. And starting at the top, this JJ1510, really, you know, Fortran, before it allowed you to do dynamic memory allocation, you had to kind of predefine all of your variables. So I learned to write Fortran a long time ago, and I just continued to do this. Maybe I should update this code using Fortran 90. But so JJ is the total number of spatial dimensions. J max is the number of materials, which is 7. And then N max is the time steps. In order to keep my arrays small, it was more efficient to have 2 forward time steps and keep 2 past time steps, and then just flip-flop them or advance them at the end of one iteration in order to avoid building very large arrays. So it keeps my memory usage down. So if you look here, there's just a bunch of declarations. This is just standard Fortran with integer, and then real 8 is double precision. Then we come down here to some kind of hard-coded variables. These are just associated with the artificial viscosity using von Neumann type artificial viscosity. This is the void pressure. I set it equal to 0. This is a contact flag that I use to let the code know when it's being when there's contact involved. This is some debug stuff that I put in there. So if you turn debug on by setting this flag equal to 1 here, then you'll start to get echoes to screen, and these echoes will commence after so many time steps, and then you can specify which node you want everything echoed to screen. This D is defined as 1D planar, and it's really using his nomenclature right here with the D equals 1, D equals 2, and D equals 3 for planar, cylindrical, and spherical. Let's see, this is the initial time step. It has a von Neumann, it has a Courant stability criteria built in, so the time step will vary. And but initially I just set it to something small, so just so we can get going here. Now these are kind of obvious number of iterations to skip before you echo to screen. You don't want to write to screen too much. That I/O is costly. And then this value is how many time steps do you want to skip before you start writing to file. And then this is how many skips do you want to do before you start writing to file, after you start writing to file. And then this AMR I've never really developed, but it's supposed to be some adaptive mesh refinement. All right, so the code proceeds by first kind of zeroing everything out. Just depending on what compiler you use in Fortran, it may or may not do a good job of that initially. So I zero it all out. Then it comes in and it reads the input file, ko.in. We talked a little bit about this in a different video, but there's the read for the material configuration. It pulls that in, and then here is the, and then it echoes it to screen here. And then here's the read for the input. So as I mentioned, the boundary condition, sorry. And as I mentioned before, you can see that it's going to continue to read materials until it finds until it gets a blank line. And if it gets a blank line, then it's going to jump out of this routine, go to 6. Sorry about the go to statement there. But it jumps out of the read and then proceeds with doing the input for the boundary conditions. So it comes on down and it reads the blank lines, and then it basically here reads the boundary conditions that you input, and then it moves on. So the next thing it does is the discretization loop. This is where it divides up the material length into the number of nodes that you set and then assigns mass to that. Really, that is kind of mass zoning. That is this first step within Wilkins formulation. And this being a Lagrangian code, those masses won't change for the entire run. So we're only going to do this one step once. And then as we iterate, we'll start with equation 2, equation of motion. So it's just doing discretization, and it will eventually here assign all the mass to the nodes, and then it will print it to screen. And then here it's just running through and calculating the basic initial properties for all of the nodes and assigning those. All right, here's where it writes it all to screen. If you get tired of seeing that, you can comment this out. So here's the beginning of the main loop. This is basically where it iterates the equations of motion on down. And I've got these flags set in here. If I don't want to echo certain things or do want to do certain things, then I can set them on and off. Here, by turning this 1 equal to 0, that means I've basically turned everything off within this if loop. And this if loop is the contact check. So that means if you started the flyer with a gap between the flyer and the, you started the simulation with a gap between the flyer and the target, then these nodes would have to come together. And if you think about it, when the two materials hit, what you have to do is, what I did was I eliminated one of the surface nodes and then joined the those two materials together. In other words, so that the flyer, the left part of the domain, the rightmost node of the flyer would begin to then communicate with the leftmost node of the target. So it becomes a central difference node rather than a left or a right node, where it looks at two spatial positions inward to be second order accurate. So this is commented out by default, but if you set the problem up to have contact, or perhaps if you're doing a mesoscale simulation where you want to have lots of little plates stacked up that slam into each other, then you could turn this on and it would generate kind of a one-dimensional mesoscale simulation. All right, in general, what this does is it's pretty simple, really. The contact check goes in and looks to see, it calculates the spatial position R, and it looks to see if they are overlapped. If they are, it calculates the exact time step it needs to take for the velocity of those nodes in order that those two nodes that are overlapped or crossed over each other would be exactly at the same location given their velocities. And it adjusts the time step to that location. It flips on this eye contact flag right here equal to 2 so that the code later knows that this is a contact situation, and then it will remove that extra node and then join the nodes, the stencil nodes together. So when nodes are initially discretized, they are assigned a value. Every node is assigned a value, whether it's essentially a boundary condition. And it lets the code know what stencil to use. So if it's assigned a value of 0, that means it's a central difference node. Back when we were looking at the input file, these nodes, the left node and the right node in the boundary condition file, are assigned to IBCs to be either -1 or 1. This means use a second order left stencil or use a second order right stencil, respectively, for those nodes. Or it could be some other boundary conditions like an infinitely rigid wall, or just I have the ideal gas equation set up so it could just be like an inflow boundary condition. So it's similar in that every node is actually assigned a boundary condition, and so you'll see that within the code, so that it kind of knows, oh, this is an internal boundary condition, this is an internal free surface, I should say. Those are the -2s and the -3s, or the +2s and the +3s, and it's looking out for those maybe to have contact, whereas the -1s and the -2s are the far left, far right. So they would never have contact. So that's really the difference. So if it detects that nodes would overlap within this time step, you can see here that it's going to, right here, it's going to then determine, okay, contact has occurred. I'm going to flag this particular iteration, and I'm going to calculate the perfect time step I need in order to have these two materials that are going to contact each other exactly meet. All right. None of that is in Wilkins' book. I kind of just added all of that so that we could get it. I could do some more advanced problems. So here it is here. If it senses that eye contact is going to happen, here's where it's calculating the exact time step it needs. If eye contact is not going to happen, then it's just going to use whatever time step it was using based on the Courant stability criteria. Okay, so we're coming in here to this first sort of equation, the equation of motion. Here's our boundary condition check. You can see what it's doing is it's got a delta t. And if it's a leftmost node, it's going to use the left side stencil, which is described in Wilkins' book here, and boundary conditions right here for the left side or the inside, and then here's the outside. So you can see it's using J-1 information or J+1 exclusively on the left and right, so that it can do the finite difference. So that's what's going on here. You can see if it's a -1, it's using information in the plus direction, and if it's a +1, then it's using information in the spatial negative direction. All right. These are the various contact nodes. They pretty much do the same thing as the free surface nodes do. Here's my rigid infinite wall as a boundary condition 4. That's kind of an undocumented feature here, undocumented in the sense that I didn't list it right here. I guess I did. Okay, I guess that's documented. And then finally, if it senses that the node is, or if it sees that the node is a 0, that means it's a regular central difference node, and it's going to follow what's here in this book, in this section right here. So you can see what it's doing. First it's going to calculate, well first I should go back. So the first thing it did was calculate all of the sigmas, which you can see is specified right here in the appendix. And then really it's about calculating phi and beta, and then ultimately using that information to calculate the future time, the half-time step for the velocity. As you can see, if you look at the boundary condition, you're really just calculating phi and beta and then calculating the velocity. So when we are looking at node 0, that's a central difference. We're applying this stencil here that's under equations of motion. Here's our central difference. So we've got our sigma r and sigma theta, so we're just going to calculate phi of j and beta of j. That's essentially what we're doing here. And then we calculate the future the future velocity. Okay, so that is the majority of step 2. Now we're going to move on to step 3. Now remember, we still could be in the middle of contact here, and we'll resolve it here at step 3. So this is saying if you're not equal to 9, and 9 is reserved for those nodes that we have these typically 10 or 20 extra nodes that I throw into a simulation. If you notice in the input file, I've only specified 1,500 total nodes here, but JJ at the top of KO was specified at 1,510. So there's 10 extra nodes, and when you do plotting, you'll see that there are nodes at 0, 0. 0 at the location r is equal to 0, and it'll have 0 stress and 0 pressure. These are these extra nodes, and they're used for SPAL. So just like when materials contact, I need to take a node out and then connect the stencil with that node that used to be a free surface so that it's now a central difference node. If they SPAL apart, I need an extra node to pop in there in order that the left and right node will be free surfaces. And given that I wrote this code such that it doesn't have dynamic memory allocation, I needed to define the arrays. All right. So if you're a regular node, if you're not one of the reserved nodes, so if you're not equal to 9, then carry on here. Here's a debug block. You can see what it does. If debug is on and endCount is greater than or equal to ndebug, then it's going to just echo a bunch of stuff to screen. But if we come on down here, begin the connection of nodes for contact, so it prints a bunch of stuff to screen like, oh, look, we're going to contact, and here's the left and right node information. And essentially, right here is just shifting the entire array for all of the data on top of each other, because those two nodes then should have the exact same characteristics. They should be free surfaces traveling at the same speed at this point. So it does that, and it reorders the array for us. Then it does a kind of a check, a neighbor check, to make sure that there are no nodes overlapping. And if everything's good, then we proceed to finally to section 3. All right, so it gets easier after this. Section 3 is the relative volume. You can see it's just following straight up here. It's calculating V and R. Here we are, V at n plus 1, j plus 1. So that's here at n plus 1. That's a half step. and then, sorry, n plus 1 is a whole step according to Wilkins. And so that's this line right here, and then I calculate the intermediates just by taking the averages. I do that for most of the nodes just so that there is data in there. If you plot them, there'll at least be average data in the intermediate node. So this is a, what is this called? A staggered mesh in time and in space. It's just it's just the scheme that he used to do this discretization. All right, so calculates the volumes, and then it calculates, that's at the future times, at j plus a half, and at r it's updating the velocity and the position. Here's the velocity strains, epsilon dot, and these are at half steps in time and in space. So that's why these are at 1, n plus 1, j plus 1, and then it calculates these guys. Now here's the stresses. Calculating first the stress deviator, section 5. So it's kind of labeled here in some reasonable way so you can see that this is section 5A. Calculates all of the deviatoric strains, S1, S2, and S3, and then it calculates the averages just to fill in the staggered mesh. If it's a gamma law ideal gas, then it can't sustain strain, the deviatoric strain, so it calculates them a little differently. Now we go to the von Mises yield condition. So it made more sense for me to move this pressure equation of state down lower in the scheme. It doesn't use pressure at all here until a little bit later, but energy is in the pressure equation of state. So I moved it past, I moved the pressure update past the energy update, mainly because you can see it needs the future time of energy here. So I decided to put it down, down below. So here comes the von Mises yield criteria. It's calculating the yield surface here, the distance to the yield surface, and then comparing, are we outside of the yield surface? And if we are, then we modulate the stress deviators. So that's what's going on here. I'm calculating my K value, and then here I'm calculating this XX as a dummy variable to calculate the distance back to the yield surface. And so here we're placing the deviatoric stress back on the yield surface. And then I do that both at the current time step, the half step, and the whole step, just so that I have all of the data. Now the artificial viscosity, that's 7. So we're here now in Wilkins formulation. I'm moving through this, calculate the artificial viscosity. It's pretty straight up. Didn't modify that at all. Here's the energy equations of state that I talked about in a different video, that you can place the equations of state. That would be here in the KO input file IEOS. So if IEOS is set to 1, 2, 3, 4, 5, 6, it's going to utilize various equations of state. So for example, this block of code here is for Nigro-Nissen equation of state. And you can see here's the gamma law, ideal gas equation of state, the gamma equation of state, and so forth. So just skip on down here. Snowplow equations of state, and so forth. Now here's this 5b. So now that I have my energy updated, I now update pressure, because you can see that pressure isn't really used at all until you get down here. So pressure here is being used at the current time step. So I thought it made more sense to put this down below. And again, this is equation of state dependent, so this would be the equation of state for the Meagher-Neison equation of state. Here's the formulation, and then here's gamma law, perfect gas and ideal gas. So you can see this IEOS variable is the flag for that particular material. So you could have mixed materials, like you could have aluminum hitting, you could have a Meagher-Neison aluminum hitting a perfect gas nitrogen if you wanted to. That's not a problem. So it's just looking for the various flags to determine what kind of material it is. So we'll move on down past the equations of state, and we're pretty much, I believe that's it for the mathematics of the problem. I was interested in temperature and entropy, so I included this entropy and temperature calculation. You can see entropy is being generated just from the deviatoric strain, so that's good. And then temperature is just simple. It's being calculated from the energy, C sub V times T is equal to the energy. So it's just calculating it for reference. And then I wanted to kind of do some total energy checks and things like that. So I included this section of the code here where I calculate energy and pressure just to see what's going on here. I did include this SPAL section, which is discussed in Wilkins' book here in the appendix about opening and closing voids. And I compare it to the pfrac value that you put into the input file here. And so if you exceed this value in megabar, then it will separate the material. So a central difference node will get turned into a left and right node. And you have to do the shifting again of the indices, which you can see is what I'm doing through this section of the code. Alright, so we'll skip on down here into the SPAL section, and now we're into time stepping. So that's section 9 of Wilkins' book here. And yeah, it's pretty straightforward. It calculates the local sound speeds, trying to find the fastest velocity and for the mass velocity, and then the shock velocities, and making sure we don't transit a wave across a node. And so that's pretty much the output of, or that's pretty much the end of that iteration. So now we can output the screen if we wanted to. Here I'm summing up the energy, the velocity, the kinetic energy, the momentum, and that's part of what's being outputted to the screen, just so you can see it. There's the write to screen. And then we output to our file. This is our write to file, which I think I discussed in an earlier video. But here's our write statement with all of the variables that go to ko.out. And then here's where finally I update the solution. So I'm shifting things like un plus 2, that's a full time step in the future. That becomes our current time step, and then n plus 1, which was our half time step, becomes our backwards half time step. So that's our update to the solution, and then that's the main loop. And if we're still less than our t-stop time from ko, the input file there, 1.54, then we'll continue to iterate. That's the end of the file, and that's the end of the video. All right, thanks.